Welcome everyone to the Intel Network Builders webinar program. Thank you for taking the time to join us today for our presentation titled Building Next-Gen CDNs for Tomorrow's Critical Streaming Workloads. Before we get started, I want to point out some of the features of the BrightTalk tool that may improve your experience. There's a questions tab below your viewer. I encourage our live audience to please ask questions at any time. Our presenters will hold answering them until the end of the presentation. Below your viewing screen, you will also find an Attachments tab with additional documentation and reference materials, including a number of websites and documents mentioned in this presentation. Finally, at the end of the presentation, please take the time to provide feedback using the Rating tab. We value your thoughts and will use the information to improve our future webinars. Intel Network Builders webinar series takes place live twice a month. So check the channel to see what's upcoming and access our growing library of recorded content. In addition to the resources you see here from our partners, you'll also find a link to our comprehensive NFV and SDN training program through Intel Network Builders University. Today, we're pleased to welcome Paul Johansson and Assad from Varnish Software, and Nash Kleppen and Tushar Gohad from Intel. Paul is a senior developer and product manager from the Varnish Enterprise product. He has worked in Varnish Software on highly optimized HTTP caching technology since 2013. Assad has worked as a C developer in Varnish Software since November last year and has used some of his time on the work he's presenting today. Assad's master's thesis was on improving the TCP implementation in the Linux kernel. Nash is a solutions engineer with Intel's Data Platform Group. He has been at Intel working on distributed storage performance for the last 7 years. His most recent work has been focused on CDN platform and software performance analysis and optimization. Tushar is a principal engineer with Intel's Data Center Group, leading CDN and edge storage initiatives across Intel. He's been working on the open source networking and storage related technologies and solutions for a couple of decades now. His recent contributions have been to CDN architectures, including cloud native, edge caching software architectures, distributed storage stacks, and networking in the Linux kernel. Welcome everyone, and thank you for taking the time to join us today. Nash, I will hand it over to you to start off.
All right, so today we plan to cover a few topics. So there will be a little bit of background on how we got to the current state of CDN and CDN performance, a little bit about how you should consider a system that you're choosing to use for a CDN, some of the design considerations in the system, some features and capabilities in Varnish Enterprise, NUMA awareness in Varnish Enterprise, some features and capabilities in third generation Intel Xeon scalable processors. And then we'll get into the benchmarking that we performed on this software with these platforms as an example of what can be accomplished. There's been an explosion in the amount of video and live streaming consumption, particularly in 2020 during the pandemic. And as these users that are using these CDN services demand higher bandwidths, such as 1080p or 4K, that increases the performance demands on a CDN. Additionally, hardware has caught up to a point where it drives an increase in software efficiency on those systems. 100 gigabit E and multiple 100 gigabit E links greatly increase the importance of the efficiency of the software that you're using. Previously, you would not have noticed some of the performance constraints. So the goal of this collaboration with Varnish is to improve the performance per TCO and performance per watt of edge caching servers using highly optimized software and optimized systems. This joint work will include an Intel Select solution, as well as optimizations in the Varnish software stack that improve CPU efficiency. So let's get into CDN system designs. So there's some overall trends in storage systems that have started to appear over the last few years. There's an increasing demand for the use of NVMEs in these storage systems. 100 gigabit Ethernet at the edge has caused a significant increase in consumption of NVMEs to keep up with the increased networking capability. Additionally, more servers are available that support a lot of flash devices. And some of the workloads that these are relevant for are CDN as well as scale-out storage such as Ceph. So these high-performance storage systems, they can be single socket, but if the performance targets are greater than what can be supported with a single socket, a dual socket system is necessary. With a dual socket system, NUMA has to be taken into account. So in Intel systems that are dual socket or four socket, the bus that interconnects the CPUs is called UPI. Typically, with these workloads, UPI has enough bandwidth to support the workload. However, the cost of traversing NUMA domains on a regular basis adds latency to that transaction, and that compounding addition of latency can become an issue. That latency is most apparent when you're using very efficient software, NVMEs, and multi 100 gigabit per second networking links. To get the most out of a dual socket system, a NUMA balanced server is required. Most systems are targeting a more general purpose application, targeting more compute heavy workloads that aren't as dependent on I/O, and tend to favor socket 0 over socket 1. So this is what a cartoon diagram of what a system that has NUMA looks like. So you have one or more CPUs, in this case 2, and as well as some memory. Your I/O devices are distributed across those NUMA nodes, not necessarily in the fashion that is most optimal. So in this case, if we were to run an application on socket 0, it has direct access to the NIC and some of the storage, but 6 of the NVMe drives are on the other socket. And so we will regularly traverse UPI to get to those I/O devices on socket 1, as well as to access that memory. So if we take a look at some examples of the cost of NUMA in an application that is heavy on I/O. As you can see here, we have a system that is using 2 sockets, 1 NIC, as well as some NVMEs. And what we see here is as the transaction flows in from the NIC, the application is running on CPU 0 and using memory on CPU 0. But the drives that have the data that the application requires are on CPU 1. So we go back to CPU 1 to access that data, and then we go back to CPU 0 for additional processing, and then out onto the NIC. This is typically about a 30% cost in terms of performance on the system that was tested for this. If you look at it another way, what if the NIC is local and just the NVMEs are remote? So the transaction will come in on the NIC, it will hit CPU 1 for some initial processing. It'll go to CPU 0 to retrieve the data from the NVMEs. That will return to CPU 1 and go out on the NIC. This is also about a 30% impact. And for this case, Nginx was used to show this, but you'll see this type of behavior in many applications. As I previously mentioned, in a typical dual socket system, I/O and I/O performance is not really the most important design consideration. Most applications tend to be compute bound. And so I/O is sometimes sacrificed for additional flexibility in system configuration. This imbalance in I/O in these typical dual socket systems makes it difficult to extract the performance from the I/O devices, the processors that you've already purchased. For instance, in this example here, in this diagram, there are 4 NVMEs on one socket and 6 NVMEs on another socket. This means that if your application tries to evenly load CPU 0 and CPU 1, CPU 0 will become constrained by the NVMEs first and stop scaling up in performance while there's additional CPU remaining, whereas CPU 1 has additional NVMEs to support additional performance. So here's some of the configuration details for those experiments, if you're interested. And now I'll hand off to Paul to talk about Varnish.
A picture of the Varnish role when serving assets over HTTP. Instead of having the clients on the top contacting a conventional web server, you put a caching layer in between. And this is Varnish software. You can see that the traffic between the client and Varnish is HTTP, and then Varnish uses HTTP to connect to the origin. I have represented the clients by computers and a cell phone, but it could just as well be an app on the TV or anyone streaming video in different ways. Varnish is infrastructure software. So it kind of bridges the software and hardware. Yeah. I don't know what to say. Anyway. Right, so this is the basic picture. Let's go to the next slide. This is a list here of some of the features in Varnish. And it is indeed just a selection. There are many other features that I could list, but this is just for giving you an idea of what Varnish can do. It is an HTTP cache, as I mentioned on the previous slide. It has streaming and request coalescing. In this context, streaming means that it refers to the situation where the content is served to the clients as they are read from the origin or backend. This will lower latency, and it will avoid that the bandwidth usage fluctuates. Request coalescing is when two clients arrive at practically the same time, asking for the same resource. And the first one will generate a request to the backend, and the other one and wait for the response. While the other way, other client will also wait, and then when the response comes from the backend, both of these clients will get the content in a streaming manner. So I will not go into more details about this, but the point is that when you have a cacheable response, you can get the optimal behavior for the clients. And this is partly one of the reasons why you want to use a cache at all. You don't want the microservices to have to worry about these things. You just want them to be able to tell the cache how long an asset should be cached. Then the second bullet point, the RFCs refer to the HTTP specifications, and in particular, the rules handling caching behavior. So sometimes the origin will provide correct details about how long something should be cached, but in many cases, you need to override that to fix the backend's wrong usage of the RFC, essentially. And you do that through something called Varnish Configuration Language, or VCL. And the VCL, it will provide lots of flexibility. It can do other things like routing. It can manipulate requests. It can even have a WAF, that's a web application firewall, and you can implement business logic like a paywall inside of the configuration language. The cache is based on memory, if you want that. And this is shared with the open source Varnish cache product. But if you need storage-based cache, you need Varnish Enterprise. And this is, of course, what Nash just showed you in the pictures. The cache will be on the drives, and you will have a cache size which is much bigger than the memory you have on the servers. And then you also have very high performance in Varnish. And I will talk about why Varnish is fast on the next slide. So first of all, Varnish works well because it works with the current hardware and software. We routinely do experiments and try to adapt the latest technology to keep Varnish fast, and this what we're talking about today is part of that. Okay, so Varnish has a threading model which includes very few context switches. So when a request is received from a client, you have as few context switches as possible. You get in the request, you read it, you handle everything, set up all of the buffers that you need to send to all the bits and parts of the response, and you send that with a single call to the kernel. And then everything gets shipped off. Part of this is minimizing memory copies, even though memory copies are fast, in quotes. It is a significant cost when that's what you do. When you try to move lots and lots of bytes really fast, you want to avoid these memory copies. You also want to avoid locking too much. So you want to have parallelism that is pure, and where locks are kept as short as possible. And then finally, Varnish uses modern APIs, and in particular, MSE, which is the massive storage engine, which is used in these experiments, uses asynchronous direct I/O. And the idea with this is to take control over what is in memory and what is on disk, and not let the kernel do its job. The kernel is smart, but it doesn't know everything which goes on, so it can't do the right thing at all points. And Varnish uses modern APIs to help the kernel do the right thing, or not let it slip up, actually. And until recently, we haven't done anything related to NUMA, but now we do. And the next slides will be presented by Asad, who did much of the work with the NUMA improvements in Varnish.
Yes, I'm going to talk about the work we did to make Varnish NUMA aware in our Varnish Enterprise product. And here, this slide shows a screenshot of the process counter monitor tool from Intel to show how our changes in Varnish improved performance. Let's talk about how we got to this point. During our internal testing on dual socket systems, we saw that Varnish pinned on one of the CPU socket was outperforming Varnish running similar workload on both sockets. This made us curious, and we quickly discovered that most of the CPU cycles were spent inside the kernel, busy looping over a spin lock. We started to read up on dual socket systems and NUMA performance. We came across process counter monitor tool, which I described above, and it gave us details on inter-socket communication, or as Nosh described, the UPI bus between the CPUs. And this tool actually revealed that some traffic were going on, but reported the link being far from fully utilized, as you can see in the picture on the left. However, all traffic over the UPI bus has a cost in both CPU cycles and added latency. And that we were seeing when we actually did one single socket performance testing compared to dual socket. And while the link has plenty of bandwidth to spare, as Nash described, we did notice that a huge amount of memory access was happening on the remote socket, and that is not ideal. The next step we did was to look at how Varnish managed memory and how we can align with the best current practice with regards to NUMA. And let's go back to the graph and see and try to explain what's going on here. The main point here is that the UPI traffic has been reduced from the left to the right, and this means that the latency and memory is kept local, which is good. And if you see on the left hand, this is before and this is after, and you see that this shows the UPI transfer from one is sending, one is receiving on the bottom. 2 lines on the bottom is receiving, the 2 on the top is the sending. And you see that this has been reduced compared to the left side. And in the middle, you have the timeline, which is kind of a snapshot into that timeline on the left and right. The reason for the transfer to be less on the receiving side is because on the sending side, you are actually sending a lot of metadata, which includes non-data transfer. I will now go through the changes we made to achieve these results. In Varnish, we have a notion of a thread pool, which is used to partition the work that is done simultaneously. In NUMA Varnish, we instruct the kernel to run all the thread in one pool on a specific NUMA node, which is typically a CPU socket. Without NUMA awareness, the kernel schedule decides which socket run which worker thread. While the kernel tries to get the scheduling perfect, it is not good as if application is NUMA aware. And the figure shows how the pools and their worker are organized and configured by default. By default, Varnish runs 2 pools. And NUMA awareness, we enforce the number of this to be equal at least the CPUs available on the system. Each pool has around 100 workers to 5,000 workers, and that's the default, but you can change that if you want through a Varnish admin tool that is included in the Varnish installation. And the number of workers can go up and down depending on the load on the server or how much kind of work there is for Varnish to do. So of course, pinning works to a specific node is not enough. We also need to make sure that the work assigned to each pool is somehow local and does not interfere too much with the work schedule on the other pool. So they have to stay locally. Yes, I will move on. The acceptor is a special kind of a worker inside the pool. The idea is doing the work locally, take one step further and make sure that when connection comes in from a NIC, we make sure that it's destinated to a CPU socket that is also on the same NUMA node. And each thread pool has one of these acceptors. And what we did was to instruct the kernel to say how this scheduling happens with regards to where clients go in using first we had to set SO reuse port flag, and then we had to load in a eBPF program to instruct the kernel to say that the NUMA index is used to as an index to which socket it's going to deliver to the client. And a BPF program is a user space program in Linux, and it allows allows the application to control decision making that happens inside the kernel. The result is that all work from this connection is carried out by a NUMA node corresponding to the network interface, and this again reduces the UPI traffic that has to be done. But we can of course do more than this. We will look more into this in the next slide. The next step we did was to look into the buffering that is happening in Varnish, and first thing we did was to make sure that all buffers that are of significant size are kept local. And in Varnish, there is kind of a strategy to keep memory buffering do as little allocation as possible and recycle buffers as much as possible. And what we did was to make sure that these buffers are recycled in a NUMA fashion and not across domains. And this includes TLS buffers and also HTTP rec and response crash buffers. All these are kept locally. Then, of course, in order to run this, you will need a recent version of Varnish Enterprise 608 R2 or newer. You will need a recent kernel version, at least 4.6. This in order to run the BPR program, and you will also need some runtime. You have a runtime dependency on libnuma, and that means you have to, or this should be fine, but it's good to know that it's going to be installed with the installation of Varnish. And the future is currently behind two flags. One is called the reuse port, and other is NUMA aware, and both needs to be turned on for this to work. You can actually use reuse port alone, but that will not bring the NUMA awareness you need. So currently this is experimental. This means that we haven't decided if this is the correct way to do it with regards to the parameters and stuff. And other than that, it should be stable. Also, the hardware needs to be configured in a way which allows this, and in order to succeed in reducing the UPI traffic. And that is what Nash is going to talk about next. And be aware that if you run Varnish on a single NUMA region system and NUMA aware support is requested, Varnish outputs a warning and continues as if nothing has happened. Yeah, there you go, Nash.
All right, thank you, Asad. So previously I talked in general about what you would want to look for or want to avoid in choosing a system for a CDN or a distributed storage system that you want to run with very high performance. So now I'm going to get into a little bit of the details. So for these experiments, we use the latest Intel Xeon scalable processors, so the third generation. And these have some features relative to their previous generation that are particularly important for CDN applications, as well as some other storage applications. But the primary focus today is CDN. Relative to previous generation, we have increased memory bandwidth, partially due to an increase in memory frequency, and partially due to an increase in memory channels. We also have PCI Express Gen 4, which offers double the throughput per lane of PCI Express Gen 3. In addition to there being more lanes with these processors than the previous generation of processors. The core count on these is also increased relative to the previous generation, along with cache size. These processors also feature new extensions to the Intel Advanced Vector Extension 512, otherwise known as AVX 512, and Intel Advanced Encryption Standard New Instructions, otherwise known as AES-NI, that can improve crypto processing. Additionally, these processors feature Intel SGX for protected execution in cases where that is desired. These processors are included in a program called Intel Select Solutions, and there's one of those solutions is for Visual Cloud Delivery Networks, otherwise known as CDN, that provides pre-validated configurations based on these processors to enable faster delivery of such a system running these types of services. These solutions are available particularly for CDN, in both single socket and dual socket configurations. Additionally, these processors can be used with some Intel I/O devices. In particular, we used the SSD D7 P5510 NVMEs, which are PCI Express Gen 4 by 4 NVMe drives. We also used Intel network adapters. We used the E810 CQDA2 and the E810-2 CQDA2, 100 gigabit per second networking adapters. So in a performance optimized dual socket system, for this type of work, what would I like to see? What would I design for given the opportunity? So if I'm going to use a dual socket system because my performance requirements scale beyond what a single socket can do, I want both sockets to be evenly loaded with I/O devices so that I can get the most out of the CPUs that I install in the system. So the diagram here, we have that case. Each CPU has 6 NVMEs, and each CPU has a NIC. Now, depending upon your exact configuration, you may have more NICs or more drives or fewer drives and even more NICs, but the overall concept is the same. For an I/O intensive application like this CDN workload, you would like both sockets loaded evenly with I/O devices. And then let's talk about a performance optimized single socket system. In the cases where the performance of the single socket is sufficient and the power benefit, the reduced power consumption, as well as the reduced cost is preferred. So many single socket systems are cost optimized rather than performance optimized. The system that we're using here, and we'll get into the specifics of model numbers and manufacturers later, but the system that we're using here is a single socket system that enables us to install 2 by 16 NICs, as well as 8 NVMEs. Now, in this case, this single socket system allows us to not have NUMA considerations. However, not all single socket systems are single NUMA. There's an important distinction to be made between sockets and single socket or dual socket, as well as single NUMA and multi-NUMA. So now let's get into our benchmarking results. Okay, so as I previously mentioned, I would get into a lot more details of the hardware that was in use. So for the single socket test system, we're using an Intel Xeon Gold 6338 processor. We're using 8 of those P5510 NVMEs, and we're using 1 Intel E810-2 CQDA2 NIC. That is a 2 by 100 NIC, so for a total of 200 gigabits per second. We also have the system populated in a 1 DIMM per channel fashion so that we get maximum possible memory bandwidth. And for those interested, the specific system in use here that offers all of this I/O in a single socket package is the Supermicro Sys 110P WTR. So this single socket system here, as you can see in the diagram, we have our NICs bonded. So we've got a 2 by 100 gig line rate on that single IP address. We will have a content origin. That content origin is not in the data path for these tests that we're about to get into, but it was used when the cache was being populated. For these tests, we have fully populated the cache, and all requests will hit the cache in the edge cache node. Additionally, we have 2 clients that are 100 gigabit per second capable. Obviously, a real-world client is not running at 100 gigabits per second, nor is it running as fast as it can go. These are used to simulate a very large population of real clients that are requesting video content on a regular basis once every several seconds, just to maintain a buffer and keep playing the content. So in terms of test results, As you can see here, this is a very strongly performing single socket system. We have a 200 gigabit per second line rate, and with all of our traffic, all of our responses to the client being encrypted via TLS, we're able to achieve 191 gigabits per second, which is approaching the limits of what is possible on a 200 gigabit per second line rate. Additionally, this was done with a 2.46 terabyte data set on those NVMe drives, where we are selecting objects from that large data set completely randomly. All objects are equally weighted. They're also not selected in order as they would be in a real video that the client is requesting. Typically, users will want to watch, say, 5 seconds of video. It's very likely that they're going to want to watch the next 5 seconds of video. This is also done with Keep Alive enabled and 3,000 total connections. So let's suppose that the performance requirements of your CDN are greater than what that single socket edge cache node can support. Well, you can scale up to a dual socket system. This system is configured, it is a balanced system, but it is configured with 6338 processors. So the same processors we used before. The system has 12 NVMEs total instead of 8. There are 6 of those NVMEs per socket. And we have 4 100 gig NICs, 2 per socket. The system is also configured 1 DIMM per channel. And so since there's 2 sockets, we have twice as many DIMMs for 16 total. And for those interested, the system in use here is a Supermicro SYS220U TNR. The system, as previously mentioned, features the ability to be run in a NUMA balanced fashion. And so in this case, we have 2 NICs per socket and 6 NVMEs per socket. Just like the single socket system, these NICs are all bonded together, in this case 4 by 100, so that we have a single IP address that we address. As before, we have a content origin that was used to populate the cache, and we have now 4 clients to try and saturate this system. So this system, on its 400 gigabit per second line rate, was able to achieve 383 gigabits per second, which is, again, just like before, approaching the limits of what you can realistically expect from a 400 gigabit per second line rate. And this was run in a very similar fashion to what we ran on the single socket system. The primary difference is that the data set is twice as large. We have twice as many clients, and so if you have a fixed data set size per client, it'll be, well, twice as large. So with this fully random selection of objects for the clients to request, we're able to achieve 383 gigabits per second, which is very strong performance. One thing to note with this configuration and other configurations that are trying to achieve these very high throughputs is that typically we've found that enabling SNC sub-NUMA clustering on Intel processors will improve our performance. We think this is due to how Linux page cache behavior is configured by the Linux kernel. We see that we get significantly better performance when we enable that feature. So that is something to consider. For those interested, here are all of the details for how those systems were configured. I'm not going to read through this, but it is available for review. And if you'd like to learn more, there's a selection of web pages here that you can look at. There is a white paper that accompanies this talk on the first, available at the first link. I believe that is also in the attachments on this webinar, as well as several other links to the Network Builders program, Varnish's website, as well as the select solutions for CDNs that are pre-validated solutions that are intended to be easy for a customer to configure, validate, and put into use. And with that, I'll hand it back to Lillian for questions.
Fabulous. Thank you, everyone, for such a great presentation. Well, we do have a few questions that have come in while you were presenting, so let's get started on those. I'll start with a question for you, Nash. Is the performance shown here the limit of what is currently possible?
It is not. We decided in this exercise that we were going to use components and configurations that were within the reasonable limits of what is likely to be used for these types of applications. So in CDN, these cache nodes are deployed in volume and they're geographically distributed typically. And so the power consumption as well as the heat generated is usually constrained. Not all of these locations where they are installed have very high cooling capabilities, nor do they necessarily offer a lot of power for the system to consume. And so we selected processors in particular that occupy a good compromise in terms of performance as well as power consumption. If processor power consumption was not a concern, we could install higher performing processors, say the 8380, for instance, and achieve significantly higher throughput at the cost of that increased power consumption.
All right, thank you. I have a question for Assad. To be 100% concrete, which platforms are supported for the NUMA improvements?
Yeah, so usually we support a dozen of platforms, but with NUMA awareness, you are limited to what you essentially need the requirement to meet. You need to meet the requirement for NUMA, and currently we have been able to see that Debian Buster, CentOS 8, Ubuntu Bionic and Focal, and Amazon Linux support this. A couple of platforms that previously works still, but does not support NUMA is Debian Stretch, CentOS 7, and Ubuntu Essential. So not all supported, but at least a modern one that is LTS right now. So good news, I guess.
All right, thank you. Thank you, Assad. And a question for Paul here. I would like to run open source Varnish. Can I get performance comparable to enterprise on a single socket system?
Well, not quite. You can get lots of performance from open source Varnish, and you have many of the features which are selling points for enterprise are there, but there are some key features which are not present. And the idea here that Intel is selling, that we actually have very large data sets on the very edge, is not possible in open source. You need to have the massive storage engine to get all of this performance. You also need to have enterprise to get the in-core TLS performance, as we have seen here. So yeah, you can get a lot from open source, but not quite this.
All right, thank you, Paul. One more question here, not specific for anybody. A good edge caching would definitely require good load balancer. Can we hope to see a one-stop solution that would take care of LB and edge caching for a private CDN, optimized for live video delivery with DRM?
I think this is a good question. The main point is that no CDNs are the same. If you are able to have a data set where the active set is close to the size of the edge cache, and the active set is the size of the data that is is actually being accessed in a reasonable frequency, then you can actually go with this solution where you have huge edge caches and you have clients connecting directly to the caches. Of course, you can do some of the load balancing inside of the clients by sending out manifest files that are aware of the situation in the CDN, and there are many different tricks that you can do to actually have the direct connection to the nodes from the clients. But I would like to hear what Nash has to say about this, if you have any thoughts.
Yes. In my opinion, from the analysis that I've done, let's suppose for a moment that these cache nodes are being used to serve a very large city, on the order of New York City or LA or, another very dense population center where you're likely to have a lot of users. And you have multiple cache nodes in that same installation. Load balancing systems that are capable of 200 or 400 gigabits per second using the traditional methods, so using something like HA proxy, is extraordinarily challenging. In my opinion, the better approach is to manage it through routing and direct clients to the appropriate edge cache as a routing step rather than a traditional load balancing step. Otherwise, you have to go to dedicated load balancers. For, as an example, you could go to F5. And even then, achieving the performance required may be a challenge, and it adds a lot of cost. So in that respect, I would try if I had the engineering time as well as the CDN, I would try a routing-based approach instead.
That's great. Thank you both for this. We do have one last question that has just come in from the audience. You referred to performance per watt. How are you measuring this? Can you share any links that describe measurements you have made?
So for the purpose of these experiments, in terms of the data that is used in this paper, as well as the data or used in this presentation, as well as the data used in the white paper that accompanies this, power was not the focus. However, if we have the same processors and the same server, and the processors are running at TDP, and we improve performance on those same systems with a software change, in this case, enabling NUMA awareness and varnish. Since the system is the same, the power consumed by the processor is, within single digits of watts, is about the same, then we've improved our performance per watt. We have done performance per watt exercises before, but that was not the overall goal here. The goal here was the software performance improvements.
All right. Well, thank you. Thank you, everybody, all the presenters for being here today. Thank you, live audience, for joining us today. That was our last question. Please do not forget to give our team a rating for the live recording, and this will conclude our webcast.